As the Chernobyl nuclear disaster passes its 37th anniversary, its physical traces may be fading, but its consequences are still being measured, mapped, and studied, not only in laboratories or hospitals, but across entire landscapes. On April 26, 1986, at 1:24 in the morning, Reactor No. 4 at the Chornobyl nuclear power plant in Soviet Ukraine exploded during a late-night safety test. The blast destroyed the reactor core, ignited a graphite fire, and released enormous quantities of radioactive material directly into the atmosphere. The amount of radiation released exceeded that of several hundred atomic bombs. Unlike a contained explosion, the reactor burned openly for days, allowing radioactive particles to rise high into the atmosphere before being carried outward by wind and weather. From the very beginning, this was not a local disaster. Within hours of the explosion, radioactive material began spreading across northern Ukraine. Within days, it crossed borders. Prevailing winds carried the radioactive plume north into Belarus, west into Central and Northern Europe, and later across much of the Northern Hemisphere. Belarus ultimately absorbed the greatest share of contamination, receiving an estimated 70% of the radioactive fallout. Entire regions were affected. Radioactive isotopes settled unevenly across the landscape, contaminating soil, forests, rivers, crops, and livestock. Among the most dangerous were iodine-131, cesium-134, cesium-137, and strontium-90, each with different environmental behaviors and health consequences. The immediate human response was slow and incomplete. The nearby city of Pripyat, home to nearly 50,000 people, was not evacuated until roughly 36 hours after the explosion. By then, residents had already been exposed to elevated radiation levels. Over the following weeks, evacuation zones expanded outward. In the first week alone, approximately 90,000 people were displaced. In total, around 350,000 people across Ukraine, Belarus, and Russia were eventually relocated, many permanently. Entire villages were abandoned. Farmland was removed from use. Families were separated, often without clear explanations. As radiation continued to spread, its reach became impossible to ignore. 2 days after the explosion, radiation alarms went off at a nuclear facility in Sweden, more than 1,000 kilometers from Chornobyl. Soon after, elevated radiation levels were detected across Scandinavia, Germany, Austria, Switzerland, and the British Isles. Rainfall played a critical role. Radioactive particles were deposited unevenly, creating hotspots far from the reactor itself. Some areas hundreds of miles away experienced heavier contamination than places much closer to Chornobyl. In the United Kingdom, radioactive cesium settled into upland grazing areas. As a result, restrictions on sheep farming remained in place for decades. Wild foods, mushrooms, berries, and game continued to show elevated radiation levels long after the disaster. Within roughly 10 days, trace amounts of Chernobyl-derived radioactive isotopes were detected across the Northern Hemisphere, including North America and Japan. At those distances, radiation levels posed no measurable health risk, but the detection confirmed something unprecedented. The contamination had circled the globe. While international attention focused on atmospheric spread, another process unfolded quietly on the ground. Radioactive material entered food systems. Milk proved especially dangerous. Iodine-131 concentrates in dairy products, and children consumed contaminated milk before authorities understood the scale of exposure. In the years that followed, a sharp increase in thyroid cancer was documented among children and adolescents in affected regions. This remains one of the clearest and most scientifically supported health consequences of the disaster. Understanding exactly where and how people were exposed has remained a challenge. That is where modern research tools have begun to transform what we know. The MAPA, Digital Atlas of Ukraine, developed by the Harvard Ukrainian Research Institute, applies geospatial analysis to the Chernobyl disaster and its aftermath. The project integrates data from medicine, demography, ecology, and history to examine how radiation spread across space and time, and how it intersected with human life. Rather than relying on national averages, MAPA maps conditions down to the level of individual settlements. As part of this work, researchers have compiled contamination data for over 22,000 settlements across Ukraine. The atlas tracks ground deposition of key radionuclides, cesium-134, cesium-137, strontium-90, and iodine-131 from 1986 through 2020. This allows scientists to see how radiation persisted, decayed, or re-entered ecosystems over decades. It also reveals how uneven the contamination truly was. Two neighboring villages could experience dramatically different exposure levels. MAPA's data goes beyond environmental contamination. It connects radiation exposure to human health. One major focus is irradiation, how radioactive material entered the body through air, water, and food. The atlas includes detailed information on iodine-131 intake, particularly through contaminated milk. Thyroid radiation doses are mapped by age and sex, showing how children were disproportionately affected. When these maps are compared with thyroid cancer incidence, geographic patterns emerge. Areas with higher iodine exposure often correspond to higher cancer rates. These correlations provide strong evidence linking radiation intake to long-term health outcomes. The project also examines contaminated products. For example, MAPA includes district-level data on cesium levels in milk from 1991 through 2005. This information shows how exposure continued long after the initial explosion. Even years later, food remained a pathway for radiation to enter the human body. Importantly, MAPA also helps reveal how exposure extended beyond official exclusion zones. Radiation spread through supply chains. Contaminated meat, milk, berries, and wool were sometimes mixed with cleaner products to reduce detectable radiation levels. These goods were distributed widely. As a result, people far from Chornobyl, with no warning and no protective measures, were exposed indirectly. Many were never officially classified as victims. Decades later, cesium-137, with a half-life of roughly 30 years, remains present in soil. While radiation levels have declined significantly, parts of the exclusion zone remain unsafe for permanent habitation. Other areas have been partially reclaimed, though food restrictions still apply. Forests act as long-term reservoirs, periodically re-releasing contamination through fires and soil movement. When compared to later nuclear accidents, such as Fukushima in 2011, Chernobyl remains unique. Fukushima released significantly less radioactive material, estimated at roughly 1/10 of Chernobyl's emissions. Japan's coastal geography and containment systems limited long-distance spread. Chernobyl, by contrast, was landlocked, lacked a containment structure, and burned openly for days. This allowed radioactive material to rise higher, travel farther, and settle across continents. Today, projects like MAPA continue to refine our understanding of Chernobyl's reach. They do not provide simple answers. Instead, they reveal complexity, variation across space, time, and populations. They show that radiation did not spread evenly, and its effects were not uniform. Some communities were devastated, others were touched lightly. Many fell somewhere in between. What Chernobyl left behind is not just an exclusion zone, but a data-rich landscape still being interpreted, a disaster whose footprint extends far beyond the reactor itself, and a reminder that when radioactive material is released into the open air, it does not recognize borders, political or geographic. It follows the wind, and its consequences unfold for generations.